All right, this is lesson 2 from our unit 4. Lesson 1 was our Desmos activities, so if you were gone for that, make sure that you make arrangements to make it up during homeroom sometime. So before we go on to our topic for day 2, I would like to just refresh your memory on the Desmos activity. So what we talked about, primarily what I want to make sure you have is the vocabulary. If we have a polynomial function, it could be in standard form, like this top one. 2x to the third plus 5x squared minus 28x minus 15. That is in order from the highest degree term to the lowest degree term, called standard form. If we take this polynomial and we factor it, this is another form of the same function. It's called intercept form. Now the reason that it's called intercept form is because each of these factors reveals one of the x-intercepts. This one reveals -1/2, and then finally 3. So it's called intercept form because it shows us what the intercepts of the function are. Not just the intercepts, though. It also tells us some other things, and they're, again, all really closely related, but when we think about each of those factors, each factor corresponds with a solution, sometimes called roots or zeros of a function. So the zeros, they're called zeros because they are the values that make the function equal to 0. So our first 0 is -5, our second 0 is -1/2, and our third 0 is 3. And again, these are the same as the x values of the x-intercepts. So when you hear the word 0 or root, those correspond with the x-intercepts and each of the factors of the function. Some of the factors in the function might be repeated. They might have what we call multiplicity. So multiplicity of a factor just tells us how many times that factor appears. So here's a g of x function in standard form. If we wrote that in factored form, which don't panic, you should not know how to factor that. But if we wrote it in factored form, it is equivalent to this. And you can see that the factor x plus 2 happens twice. So we can write it with an exponent that's called multiplicity 2. The factor x minus 1 happens 3 times, so we call that multiplicity 3. So if we were solving, so using the exponents is just a way of writing it a little bit like shorthand. If we were solving for the zeros of that function, we're wondering when x plus 2 squared times x minus 1 to the third would equal 0. Well, there really are only two solutions, -2 and +1, but they have multiplicity. So this first solution has multiplicity 2 and the second has multiplicity 3. The x-intercept associated with that first one is the point -2, 0. And because it's multiplicity 2, that means it's going to just touch the x-axis and turn around. It's not going to go across. And the second one, the second x-intercept is 1. And at that x-intercept, instead of touching and going across, it's going to have a terrace like this, where it gets flat for a second. Here's sort of a summary of that. So if the multiplicity is even, 2, 4, 6, it's not going to go across. It's just going to touch and turn around. If a multiplicity is odd, it's definitely going to go across from one side to the other of the x-axis. Multiplicity 1 means just go straight across. Higher odd numbers, 3, 5, or 7, make this terrace behavior where it flattens out, sometimes also called inflection. All right, so quick reminder of the fundamental theorem of algebra, which you have studied before in the past, and you know, I think, pretty well. If a polynomial has degree n, that means it's going to have n roots. So if we have an equation that's an x squared type equation where the power or the degree is degree 2, you know you're going to have 2 solutions, 2 roots. If it is degree 3, you know you're going to have 3 roots or 3 solutions. The one thing that you maybe have not thought about before is that that does include repeated roots or multiplicity. So for example, if we wanted to solve the equation x squared plus 14x plus 49, if we factored that, it would be x plus 7 and x plus 7 equals 0. So we have two solutions, negative 7 and negative 7. Well, that's really just negative 7, but it has multiplicity 2. So there are two solutions, they're just identical. So there are still two solutions. Happens twice. So occasionally you'll see that happening in an equation. Okay, so here are some of the implications of the fundamental theorem of algebra in our context today. We know if we have a polynomial equation, we know exactly how many roots it has. The degree tells us how many. If a polynomial is factorable, we can find those roots by just simply factoring it, and we'll be factoring more next time. And if we graph the function, we can see the real roots that correspond with the x-intercepts. The only problem is if they are non-real roots, if they have an imaginary part like an I, we cannot see those ones necessarily on the graph. They don't correspond to x-intercepts. And more on that coming up in the future. Today, what we're going to focus on is just polynomial functions by finding the equation of a polynomial function from the intercepts or the roots. So if I give you the roots of a function or show you a picture of the function, you should be able, after today, to be able to write the equation of the function. So we're going to start here with a pretty basic one. Write the equation of a cubic polynomial function that has zeros, -1, -2, and 3. So for each of the zeros, we can write a corresponding factor. If the 0 is -1, the factor that goes with it is x plus 1. If the 0 is -2, the factor that goes with it is x plus 2. And if the 0 is 3, positive 3, the factor that goes with it is x minus 3. So if our question just said write a cubic polynomial function with those 3 zeros, this would be such a function. F of x equals x plus 1 times x plus 2 times x minus 3. It's just in intercept form. More often than not, though, we would prefer to have our function in standard form. Well, if you have it in intercept form and you want to turn it into standard form, you simply have to multiply it out. To multiply three things together, pick 2, multiply those two. X squared plus 3x plus 2. I just FOILed it in my head. You should be getting good at foiling in your head. And then we take that result and we multiply it by that third factor. This is a little more complicated, so I'm going to write it out. If I distribute the x, I get x to the third plus 3x squared plus 2x. And if I distribute the -3, I get -3x squared. I like to stack it with its like term, minus 9x minus 6. So if we combine our like terms, we have an x to the third. Those two terms reduce to 0, minus 7x minus 6. So here is our function in standard form. Okay, I want to look at the graph of this function. Let me pull up Desmos real quick. Okay, so right now I have, zoom out a little. Right now I have the function shown f of x is typed into Desmos in intercept form. So you can see if I switch over to g of x, I named it something different just because. You can see that those are actually exactly the same function. Just two different forms. F of x is in intercept form, g of x is in standard form. So here is g of x. Now g of x is not the only function. X to the third minus 7x minus 6 is not the only polynomial that goes through those three intercepts or has those three roots. There are many, 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 many functions that do. Here's one shown in green. It's just the same function but stretched. Or here's one shown in purple. stretched by a factor of 1/2. The orange one also goes through these 3 points, those 3 zeros. It has a stretch of -1/2. And really, we could stretch it by any number. Here's showing you many of those functions. See how it has always the same x-intercepts. Well, the x-intercepts stay the same, but the y-intercept, you might notice, does not stay the same. So if our question is, just write a cubic polynomial with these zeros, we could have picked a different function. We could have, say, stretched the whole thing by a factor of 2. We would have 2x cubed minus 14x minus 12. That would be stretched. It has the same zeros as the original function. But sometimes we don't have a choice. Like on this one, we did have a choice. We could have stretched it if we felt like it. This one, we don't have a choice. Okay, it's not saying write the equation of this stretched out function. It's not saying write the equation of this one with those zeros. This one is very particular. Both the x-intercept and the y-intercepts are shown to us, and we need to use that information. We're going to start out exactly the same way as we have been. The only difference is we add the last step of checking the y-intercept. So first, let's write down our x-intercepts. They are -2, 3, and 7. Here they are, -2, 3, and 7. And for each of those, we could write the factor that goes with it, x plus 2, x minus 3, x minus 7. And to put it into standard form, we would just multiply it out. So we're going to multiply maybe these first two together to get x squared minus x minus 6. Again, I just FOILed it. If you need to write out all the steps of foiling it, you should do that. But you can probably get to the point where you can do most of those foiling in your head. And then we need to multiply that by the x minus 7. So if we distribute everything, we get x to the third minus x squared minus 6x. And now if we distribute the -7, we get -7x squared plus 7x plus 42. So if we combine our like terms, we have x to the third minus 8x squared plus x plus 42. So this is our potential function. Now we did a bell work in class, which is not part of this video, but what we talked about is that this number at the end, just like a line, it tells you the y-intercept of a function in standard form. So this function that we have written has a y-intercept of 42. But our equation over here has a y-intercept of 6. So we have to think about what stretch we could use on our function that we have written to turn it into an intercept of 40 from 42 into an intercept of 6. And we stretch things by multiplying them in math. So if I want to stretch 42 and turn it into a 6, I would need to times it by 1/7. You could think of it as that we want to divide the 42 by 7 if you want, but I'm going to write it as 1/7. So we can't just times one term when we do a stretch. We need to stretch the entire function, so we times everything by that 1/7. Okay, so in intercept form, our function is going to look like, we'll put that 1/7 in front of those factors. It's the constant multiplier in the front. It's the stretch. In standard form, we would distribute that 1/7 into each of our terms, like here. That will be a 1/7 x to the third. It'll be a -8/7 x squared. And it's okay to leave that as a fraction like that. and then it will be a 1/7 x, and then finally 1/7 times 42 is 6. So you can see that by multiplying by that fraction, we now have a y-intercept of 6, just like what we wanted to match our graph. Okay, so you'll have to check to make sure your y-intercept matches if it is given to you. And again, in example 1, it didn't specify. We just had to do it on example 2 because we had the picture. Okay, example 3 tells us that there are 3 roots of a cubic polynomial, and it tells us that those roots are, and I'm going to list them, 0 and -3 with multiplicity 2. Multiplicity 2 means the root -3 is happening twice. Tells you how many times it's happening. So for each of those factors, for each of those zeros or roots, we're going to write the factor that goes with it. For a -3, it's going to be a factor of x plus 3. For the root -3 over here, hey, it's the same. We have another factor of x plus 3. And for the root 0, the factor that goes with that is just x. These numbers are essentially answering the question, when will the factor equal 0? So if we want a factor to equal 0, the factor is just x. So here are our 3 factors of the function. Now it does give us a bit more information here. The function has a leading coefficient of -1/3. We're going to come back to that in a minute. First, let's put our function into standard form. So if I want to multiply it, maybe I pick to multiply these two together first. So if you multiply those out or FOIL them, if that's how you remember it, it would be x squared plus 9, or 6x plus 9. Don't forget that you get a 3x and a 3x to give you 6x. And then that we will multiply by x. So in this case, it's a little bit simpler. We just distribute x to the third plus 6x squared plus 9x. 9x. Okay. So we have this now, and it tells us that our function is supposed to have a leading coefficient of -1/3. That means, well, right now it has a leading coefficient of 1. Well, if we want to have a leading coefficient of -1/3, in this case, we would have to multiply the entire function by that -1/3. It's a stretch of -1/3. So -1/3 x to the third would be our first term. Our second term would be -1/3 times positive 6x squared is a -2x squared. And for our last term, if we distribute that, -1/3 times positive 9x would be a -3x. So here is our function. It called it f of x, so I will as well. So it has a picture of it here. The darker one right here is f of x. I have on there also a lighter gray one. The lighter gray one is the function, what it would look like if you don't do the -1/3 coefficient. Oh my goodness, I can't spell today. So it's essentially the x to the third plus 6x squared plus 9x. So the one we wanted in particular was the one that I traced the red over. And it is right here. Okay, last one, write the equation for the cubic function shown. Well, if I look at this and I notice the two x-intercepts are -2 and +2. But this is a cubic function. It should have 3. You have to watch out for graph behaviors that give you additional information. This comes up, touches the x-axis, and turns around. That graph behavior is telling me that this one has multiplicity 2. The only thing that can make that behavior on a graph is if it has a multiplicity that is even. I guess you may guess, or you may think perhaps it's 4 or perhaps it's 6. It has to be an even number. Usually I go with the lowest number that will fit the bill unless I have more information. So this is going to have multiplicity of 2. So we've got a negative 2, a negative 2, and a positive 2. So if we write the factors out, it's going to be x plus 2, and x minus 2. I'm going to pick these two to multiply out because I noticed that it was a sum and a difference. And if I multiply that out, I know that it is x squared minus 4 because I'll have a 2x and a negative 2x that cancel out to 0. And now I just need to times by x plus 2. So if we FOIL this, we get x to the third, a 2x squared, a negative 4x, and a negative 8. Put the y equals for now. So this is so close to our real function. We just need to check that y-intercept. Right now we have an intercept of negative 8 on our function, but our actual graph has an intercept of negative 4. So we're not quite there. It looks like I need to cut this in half to make it be negative 4. So I times the entire function by that. Let's see, I'm going to do this. And again, you can't just tack it at the beginning or divide the last term. You have to stretch the entire function. So we'll be a 1/2 x to the third. Well, 1/2 times 2x squared is just x squared. 1/2 times negative 4x is negative 2x. And the 1/2 times the negative 8 gives me negative 4. And it now has the correct y-intercept that matches the graph. That is my function. And I am finished. I have adapted it to be the correct function. So watch out for multiplicities. Make sure if you know the y-intercept or if you have access to the y-intercept that you make that final adjustment. But other than that, it's really just about writing the factors that go with the roots and multiplying it out into standard form. In your notes, there are a couple more practices. I am going to I'm not going to include them in the video just so that the video is a little shorter for your pleasure. If you need some help with either of those or if you want me to help you through a couple more examples, please just come in at lunch or after school or before school and I will help you. The homework is in your notes is pink. It is 4.2 polynomial equations from intercepts, roots, or zeros. And it is due next time we meet. That is it.